Okay, so let us begin. Let me start by spotlighting myself. Okay, great. Yeah, so as you can see, I got a new eraser. Okay, so let's continue from where we were yesterday. So yesterday we saw the definitions of totally positive matrices, totally non-negative matrices. We saw some simple examples, and then we proved that every generalized van der Waals matrix whose bases are increasing and exponents are increasing is all real numbers, of course, and bases are positive. This is totally positive. Okay, and to do that, we looked at first we proved Descartes' rule of signs, and then we used the fact that the usual van der Waals matrix has positive determinant to prove that every van der Waals matrix, first of all, is non-singular, and then the determinant cannot be negative because of this continuous path. Okay, and then as a consequence, as a corollary, we showed that the Gaussian kernel, which is on the entire real line across the entire real line, so it's an R cross R matrix, uncountable. That is also totally positive. Okay. So now so there are some examples of totally positive matrices, and then here are other ways to make examples. So here, lecture 2. So first of all, let me tell you this. Basically, the trick that we used to prove that the Gaussian is totally positive can be written more generally. So let us pick up from there. The Gaussian kernel, total positive. So the total positivity of the Gaussian kernel can be shown. So was shown. Fine. Let me change it slightly. The argument to show, or the total positivity of the Gaussian kernel can be written slightly more generally. Extends or can be generalized as follows. Let's call this a lemma. Okay, good. So this is I will do this as follows. Okay, so lemma. Say A M cross N is TP, or maybe I will say it slightly in more detail. Say A in R to the N cross N. This is a matrix of real numbers. Is TP is totally positive, and let me take two diagonal matrices. One is M cross N and one is N cross N. Okay, and the M cross N, the prime N cross N are positive definite real matrices. So like I said, our diagonal real matrices are real diagonal matrices with all the diagonal entries positive. All diagonal entries positive. Then the claim is, then this is exactly the trick we used for the Gaussian. We claim that D times A times D prime is also totally positive. So this is not in the notes that I have, but the point is this is exactly the trick that we used for the Gaussians. So maybe I will ask Rajesh, if you're here, since he's here, to work this out in the tutorial session. Maybe you can add this to the tutorial problems. I will add it later on to the tutorial session problems. Okay. Great. Okay, so that is one nice fact. And so that's exactly what we use. We use e power minus sigma square xj square here for this matrix, e power minus sigma square yk square for this matrix, and this was e power plus 2 sigma square xj yk. This was a generalized van der Waals matrix, which was square, and these two were real diagonal matrices with all positive entries. And since the generalized van der Waals was TP, therefore this was TP. That was how we proved the Gaussian kernel is positive, totally positive. Okay, so that is one lemma. And now let me say, okay, now which way do I want? So this is one way. Okay, so here is one way to start with a totally positive matrix, even rectangular, and generate a new one. Okay. And so the next formula that I will tell you, or the next result that we will talk about, tells you another way, a very, very closely related way of getting to a totally positive. So, and the closely related way is we don't use these matrices. We just say that the product of two totally positive matrices is totally positive. Okay, so I don't know if I call it a lemma or a proposition. So proposition. Okay, so say, first of all, let me write down the A m cross n, B m cross k. Let's just say, let me do it the same way as that. Suppose A is a real matrix, R to the n cross n. I hope I'm getting the symbols correct. Yes. B in R to the n cross k. Now, so basically the lemma is if A, the proposition is if A and B are totally non-negative, or I can put totally positive here. So is A times B. So we know how to multiply matrices, and all it's saying is that if you take the product of two of them, then that is the case. Now the point is this is not true for positive semi-definiteness. Of course, for that we need the matrices to be square and real and symmetric. And the point is that the product of two symmetric matrices need not be symmetric. So there are several things one can do there. One can sort of replace this by the square root of A times B times the square root of A. Or one can replace the product, the usual product, by the entry-wise product, the true product. So there are other things you do for positive semi-definite or positive definite matrices. It is nevertheless true that if you look at it spectrally, then if A and B are positive semi-definite, then their eigenvalues are all real and non-negative. And then A times B, the usual product, may not be symmetric, but its eigenvalues are also all real and non-negative. And similarly for if A and B are positive, definite, their eigenvalues are all positive, and then A times B need not be symmetric, but it does have real eigenvalues, and its eigenvalues are all also positive. So that part goes through, and anyway, that we will talk about eigenvalues of totally non-negative PP and PN matrices next time. So for today, let's first, well, let's start on that. Let's first prove this. Okay, so how does one prove this? So for this, we need this classical identity called the Cauchy-Binet formula. Needs theorem. Cauchy-Binet formula. And this is going to talk about the determinants of some matrices, of product of rectangular matrices. Okay, so given, and this formula holds completely generally. So it holds over any commutative ring or over any field or complex numbers, real numbers, finite fields, whatever. So let me just state it in a commutative ring. You are free to assume this R is actually this R if you want. It really makes no difference. Is a unital is a commutative ring with unit. Actually, I don't even need the unit. It's a commutative. And let us say we have two matrices. Let's say this is R is an M cross N, the way as above, and B is an R to the N cross M. So that way. Then, do I want to say this like this, or do I want to? Maybe I should first show you an example. So then let's keep this theorem on pause. Let me first tell you an example of this theorem. And the example of this theorem is the usual matrix multiplication. So, let me give you a bunch of examples. First of all, let's say there are one row and many columns, m equals 1. So that means what I have a matrix with one row and many columns. I have a row matrix and I have a column matrix. And I'm just looking at the multiplication. So that means A is something like B1, B2, Bn. B is B1, B2, B. Okay. And then what I'm saying is I want to calculate the following. Then I want to say that the determinant of AB is what I want to calculate in this form. And it is going to be a summation. Okay. So now, well, what is the determinant of AB? Here A times B is a 1 cross 1 matrix. So the determinant of a 1 cross 1 matrix is itself. It's a scalar. So then AB equals AB itself, which is 1 cross 1. And that is literally just summation. So you see it's already a summation. And you do AI times BI. I goes from nowhere. Okay. So that's what it is. Okay.
Hello. Sir, I have a query. Is suppose R is a commutative ring.
Yes.
And a matrix A belongs to M cross N. And also matrix B belongs to R N cross M.
Yes. M cross N and N cross M. Yes.
These are different rings or same ring?
I could not hear you. Sorry.
ये एक ही रिंग है सर या फिर अलग-अलग रिंग है दोनों?
एक ही रिंग है R and R.
तो सर इसका एडिटिव आइडेंटिटी क्या होगा फिर?
0.
M क्रॉस N में ऑर्डर की मैट्रिक्स के लिए तो सर M क्रॉस N की आइडेंटिटी होगी 0 मैट्रिक्स और N क्रॉस M के लिए फिर वो अलग-अलग.
So these two are not rings. First of all, ये दोनों ring नहीं because the matrices are rectangular. ये सिर्फ additive group है. R module है actually. कोई additive group है उसका identity है 0 M cross N and 0 N cross N. Different size 0. अपना transpose basically.
Okay.
So these are not rings. These are groups or R modules, but they are and they each have their additive identity. But I don't care. I want to note that A times B is M cross N. So it is square matrix or square matrix का determinant ले सकते हैं. So then that is what we are doing. So I will write down the formula, but for now this is what it is. Okay. So now more questions. Sorry, yeah, more questions.
No, sir.
Okay, so first of all, that is what it is. So the way I am going to interpret this is by saying, since this is 1 cross 1, I look at all the 1 cross 1 matrices inside here that I can get. This one is fixed, but I look at all possible choices of one column. And here the column is fixed, I look at all possible choices of one row. And whichever choices I make here, I take the same indices here. So if it's the first column here, I take the first row, A1, B1. If it is the second column here, I take the second row, A2, B2. And I add up over all of them. And that's exactly what it is. So similarly now, let me show you the answer for, let's say n equals 2. And let's say I take n equals 3. Oh, well, actually, let's even do better. So first of all, let's take n equals 2. If m and n are both 2, then I literally have a square matrix and a square matrix. Then what do we get? Then what I'm saying is I'm multiplying something like ABCD times A prime, B prime, C prime, D prime. So I would have to take these two rows and these two columns for fixed. And but then I choose any two columns from this side. Well, because n equals 2, there is only one way to choose those columns, and that is the full thing itself. And only one way to choose the corresponding rows. So in that case, what we are saying is the determinant of A times B is the left-hand side. On the right-hand side, it is the summation over all possible choices of columns here. But there is only one choice. So there is no summation. It is exactly what I have. And so what is the matrix I get here? It is the determinant of this matrix because only one choice of columns. Get A times B. And again, we get a formula that we all know very well. So when the matrices are square, the Cauchy-Binet formula just says that the determinant is multiplied. When the matrices have one row here and one column there, the Cauchy-Binet formula is the definition of matrix multiplication. So these are both special cases, and now let me tell you the formula here. It is literally J contained in, so what is the common size here? N. J contained in 1 through N. And the size of J equals N. Okay. So you choose all possible subsets of the indices from 1 through N of the columns of size N, all possible M tuples. And then you write down the determinant of, so now from that matrix, you can form this matrix, right? Which is A M cross J. Sorry, I need some more space. So, okay, so now all I'm saying is the following. So now I take all the rows of A and I take those particular J indexed columns of A. I get a matrix A M cross J. Similarly, I get a matrix B J cross M. The columns of B are fixed because there are only N of them. So I take all the columns of B, but I take exactly the J labeled rows of B. And now these are both M cross M matrices because there are M rows and M columns, and M columns and M rows and M columns. So now I take the determinant, and that is the answer. That is the Cauchy-Binet formula. And maybe I should just point out here, N just stands for the set of all integers from that. So both here N and M get over there. N just means the set 1 through N. So those are all the possible indices for the rows, and then you take from the N so many indices for the columns. So now you see why these are special cases. Again, just to remind you, just to take a look again. So let's say N equals 1. So from the set 1 through N, you take every singleton element and you look at A1, comma, that element, A1i. But A1i is just AI. And similarly here, BI1 is just BI because there is only one column. So that means AI times BI. And these are scalars, so the determinant is equal to the scalar itself. So determinant of A1i is this, and determinant of BI1 is this, the scalar itself. So summation over all of that. Here again, you see, if you take M equals N, then how many, if this was M itself and you wanted a subset of size the same thing, there is only one set, which is the whole set. So you get A, all the rows, all the columns. That is just A, determinant of A. And then B, all the rows, all the columns, so determinant of B. Okay. And now let me show you an actual, actual use of Cauchy-Binet. Let's say A equals 1, 1, 1, 0, 1, 2, and B equals just 1, 1, 1, 0, 1, 1, 1, 0, 1. Okay, so now I have, this is going to be a genuine use of the Cauchy-Binet formula. So first of all, let us write down, let's compute and verify that this is true. So AB, what is AB? AB is 3. Actually, why am I doing this? I should be doing it nice. Right? So let me now do 0, 1, 2. Let me do minus 1, 0, 1. So these are orthogonal rows. Orthogonal columns here. And now because they're orthogonal, of course, these are zeros and this is 2. So the determinant is 6. But the other way to do it, the right hand side says the right hand side says the right hand side says I take two columns at a time. So I take the first and the second columns, so I get 1 1 minus 1 0. And then the same two, so 1 1 minus 1 0. Last get, then I take 2 3, so 1 1 0 1. And then 1 and 3, columns 1 2, columns 2 3, columns 1 3. These are all the possible choices of 2 elements out of 3. 3 choose 2. 1 3 is 1 1 minus 1 1. Of course, each matrix, the second matrix in each case is the transpose of the first matrix. So the determinants are the same. So I'm just adding up squares of this, right? So this determinant is triangular, so it's just minus, it's some plus or minus 1, the square is 1. This one is again square is 1. And this one, the square is, this one is 2, so that's 6. So that's 6 equals that 6. That is the Cauchy-Binet formula. Okay. So let us now so
Sir, excuse me.
go ahead, yeah.
One question, sir. Why, in example 3, why we are taking A and B as a transpose of one another? Can we take
Whatever you want. I just took it so my calculations are easy.
okay, okay.
Yeah. This is true for every pair of matrices n cross n cross n over any commutative. There are no constraints.
Okay. Thank you, sir.
I just did it so yeah, I can do this faster. I didn't plan on doing an example, but fine. So now so okay, maybe I'll put a fourth case, which is I want to talk about the m cross m determinant, right? So what if I know so I want actually this A is n cross n and B is m cross n, B is n cross n, right? Suppose I know that the rank, so that means that A times B is n cross n. Suppose I know that let's say the rank of this guy is less than n. The moment the rank of A is less than n, the rank of AB, actually let me make it even, let's take it even simpler. So let's not get into technicalities about rank. Let's say n is less than n. If n is less than n, then this matrix is singular. Therefore, the determinant is 0. So I want to say that the same thing happens on the right hand side. So this is the pathological case. So this is what the pathological case. If n is less than m, then the left hand side is left of AB m cross n. But if n is less than n, then the row rank, column rank, the rank of A is less equals n, which is strictly less than n. And so the rank of AB strictly less than n as well. So the determinant, of course, is going to be 0. The column space is not large enough. Okay? How about the right hand side? The right hand side says that out of n, the 1 through n, the elements, you take m many choices, a subset of size n. Well, because m is larger, there are no possible subsets you can choose. You can't choose a subset of size 5 from a set of size 3. Okay? So the right hand side therefore has no terms of the. So this is what one says is the empty sum. And by convention, the empty sum is always taken to be or 0. So that is why when n is less than n, this is not really a formula because you have an empty sum on one side, but we take empty sums to equal 0 because you're adding nothing. And therefore the left hand side and the right hand side are equal. Okay, so now let us actually prove the Cauchy-Binet when this doesn't happen. So this is the case that maybe this is the first step in the proof of Cauchy-Binet. That when n is strictly less than n, the terms are equal because it's by convention. But really the proof of the Cauchy-Binet formula applies when n is bigger equals n. right? Like this case or that case. So let us do that. So proof of Cauchy-Binet, and after Cauchy-Binet, we will prove the proposition. Okay, so n equals n less equals m is done. So we suppose, we assume now that n is bigger equals n. So now let us prove the formula. It is really just a, what do you call it? It is really just a calculation. There is nothing much to do. Okay, well, okay, so the only thing you need to remember is the things that you studied when you first learned about the determinant, namely that it is a multilinear. So it is linear in every row, every column. So that's basically all that we do. So the first thing to do is to write down explicitly using matrix multiplication what is A times B. Okay, so now let's start. I think I got here. So start on the left hand side. Okay, this is det of AB. Remember, AB is m cross n. Is det of. Okay, so the first term, one, which index, I'll just use the same indices that I use. J1 goes from 1 to n. A 1 J1, B J1 1. And then dot dot dot. The last term in this row is Jn goes from 1 to n. A 1 J1, B J1 and n. And because this is the 1 comma m n. And then similarly A2 J1, B J1 1, whatever you know what this is, this is Jn goes from 1 to n, A2 J1, B J1 m, J1 goes from 1 to n, and then keep going. Last term here, I should not bend my parentheses so much, I don't have space to write it. Again, this is J1 goes from 1 to n. I hope this is all according to the convention. AM J1, B J1 1, and here it will be AM J1, AM Jn. Oops. It should all be Jn, of course. Index of summation changes. This I write it now. It's much cleaner in the hand. Yeah. So the determinant of AB equals this. Fine. But now you see you can write down every term in this column is a summation over J1 going from 1 to n. And we know the determinant is linear in that. As long as you have a common summation, you can just take the summation outside and take a sum of determinants. The same thing for the second column, same thing for the third column, same thing for the nth column. So in every column, we have the same index of summation and the same range of the summation. And in fact, also the same the second terms. But let's just write out. So let's take the summation outside and let's take the second term outside. This is common. So I can take the Bj1 outside. This is common, so I can take the Bjmm outside. So let's see if I can write this one. So summation. Okay, so first of all, I can take J1, J2, Jn. Each of these guys belongs to n. So they independently belong to n. So therefore, this belongs to n to the n. Okay. And then I write down these guys. So that the common terms B, J1, 1. Right? And then here it will be B, J2, 2. Dot B, J, N, N. where the 1, 2, and the n, the second indices are fixed. The first index varies over all possible choices. And then the determinant of this. Now I have to just write this down. A1, J1. Oops, I think I may again need a bigger parentheses. So let's first write down the entries. So the entries are exactly what you see. A1, J1. Oops, but this one should be subscript. Then A2, J1. A-M, J1. A1, A1, J2, 2J2, AM, 2, AM, sorry, A1, JM, A2, JM. So the Cauchy-Binet formula proof is not so much an exercise in linear algebra as an exercise in summations. You really need to know how to keep track of summations very carefully. And then others. So this is the multilinearity. AMJN. Now I will put the matrix parentheses around it. Okay, so this is so you see this is a summation of all possible choices of J1, J2, J2. Sorry, question. Okay, so this is the sum over all possible choices. Now suppose let's say A1, J1, A2, J1 and so on. Then A1, J2, A2, J2 and so on. Suppose J1 equals J2. Then what can you say about this determinant? You just look at the first two columns. Suppose J1 and J2 are the same number, because you see there is no constraint that they have to be different or same. They can be independently in 1 through n. So suppose J1 and J2 are equal, then what can you say about this determinant?
0.
It's 0, right? Because these two columns are identical. The same way J1 and J3 or J1 and J4 or Ji1 and Ji2, any two J's are the same, then this determinant becomes 0. Therefore, I can just
0, yes.
Sorry, go ahead.
So actually, if you choose J1 equal to J2,
Yes.
then since we are choosing m elements out of n, so won't that affect that?
I just asked what the determinant is if J1 equals J2.
Yeah, J1.
No. You're choosing m elements, but no, you cannot. You're choosing them independently. That's what I said. Right? Therefore, there is no constraint. This is each of them separately goes from 1 to n. Independently goes from 1 to n. There are no relations how you choose J1 and how you choose J2. They don't need to be distinct or equal. You can be arbitrary in your choice. And that is why.
Then, if that is the case, then J1 can't be equal to J2. So A1.
Why not?
No, in the second column and third column of the matrix which you have written just now, whether it could be.
These two.
Yeah. If you say J1 equal to J2,
Yes. Then
whether that's possible that A1 J1 will be equal to A1 J2 when J1 equal to J2?
yes, because if J1 equals 1 and J2 equals 1, then this entry is A1 1 and this entry is A1 1 because J2 is 1.
Yeah, that's what I'm asking. J1 being 1 and J2 being 1 means that you are taking the same indices.
Yes.
That is 1 1.
Exactly. And the reason is because when you multiply A times B, indeed the same entries of A get multiplied by other entries of B in different columns.
Yeah, yes.
Multiplication. The same entry of A will occur in matrix multiplication in many cases. Not
Yes,
only
yes.
one column. That's why. It will occur in this row and in this column and this column. So that's how you do matrix multiplication. Right? The first row times the first column is coming here. So the first entries, all the entries in the first row will show up here. The first row times the second column comes here. The second row. So
Yeah,
all
yes.
again show up here. All the entries in the first row they show up here. So yes, they keep you absolutely can. So somebody needs to mute their. Somebody. Yeah. Okay, so, this determinant will vanish unless all the data. So you can replace the sum by saying distinct. Let us do that. First reduction, you can replace the sum with distinct. All the days to be distinct. Rajesh, maybe you are supposed to mute the person who's unmuted. At some point, they will be as now. One second, I just. I did it. Since somebody was muted, I just muted them. Okay. Somebody was unmuted, I muted. So, okay. So, first of all, that's the reduction. This is summation. How do I write this down? I just say all JL are distinct. If you have questions, please unmute yourself and ask me. Otherwise, let us avoid background audio. So all JL distinct. So right now, I'm not going to write anything else except exactly the same stuff. So BJ11. And then the debt of this. Should I just say something like AIJL? So here J is not going to change. It's like J1, J2, J3, but I and L are going to go 1 to L. Okay, so that is what it is. And now indeed these are submatrices of the matrix A, because now the rows are all distinct, 1 to n, and the columns I am assuming to be distinct. Okay. So now this is indeed the actual submatrix, which still may have 0 determinant, but whatever it is. Okay. And now let us write this down. Okay, so and now what do I want to do? So first of all, okay, now one has to be slightly tricky. So do I want to do ascending order first? Apparently not. So then let us write this down very carefully. This is still, now the summation stays the same, and I will just change this. Okay, maybe I'll stop. I would change this. How is the easiest way to say? So now here is the point, right? So I'm adding this up over like, so let me take a typical, let me say my J3, 1, and 5. My J1, J2, J3. Maybe even 3, 1, and 2. Why 3, 1, and 5? So I have these terms, right? Fine. So I have B31, B21, sorry, B31, B12, B23. Yeah. What do I want to do here? Okay, I want to say somehow. This is where I will get started. The M cross this thing, yes. I want to group them together. So I want to collect together the terms that look like this. Okay, for this term, what is the matrix I get here? Maybe that's the correct picture. I get A1,
3, A1 3,
right, and then A1,
A1 2, A2 3,
Tell me if it is wrong. Otherwise, I know what I'm doing. This is right, right?
Yes, sir.
Right, great. Okay, thanks. Okay, for this J1, J2, and J3. Similarly, if I also suppose I have A3, 1, and let's say I have 2, 1, and 3. Okay, as J1, J2. Then what would I get? I would get, so look, these two are different, these two are triples of distinct entries. So they both will occur as the sum and key, and you will get something. For now, I'm not caring about what expression I get here. I'm only looking at this thing. I will get the determinant here. And here I will get the determinant of, now I will get A1, 2, A1, 1, A1, 3, sorry, not B,
Two, two,
A1,
A one,
yeah.
A2, 3, A3, 1, A3, 2. Yes, sir. Yes.
Right, great. Now, if you notice these two matrices, they are exactly the same matrices up to some row permutation, up to permuting some rows.
Yes, sir.
They are exactly the same matrices, right? And that is what's going to happen the moment I have 3, 1, 2, 2, 1, 3, 1, 2, 3, 1, 3, 2, and what are the remaining ones? 3, 2, 1, 2, 3, 1. For all these 6 permutations of the same 3 distinct indices, J1, J2, J3, or J3, J1, J2, or whatever. For all these 3 factorial permutations, I will get the same determinant. So all these things will be equal up to plus or minus sign.
Yes, sir. Right, right.
And not only that, you can calculate exactly what the sign is in terms of the permutation level. So if you fix one of the permutation, let's say I fix this permutation, so that I get A11, A12, A13, A14, the usual sum matrix of A, then every other one will have the same determinant up to the sign -1 power sigma, where sigma is the permutation applied to it.
Yes, sir.
So that is what you get. 1 second, sorry. Yeah. Okay, so so I won't explain that formally, but I will write down now what this is equal to over there. And the example here should basically tell you what it is. Right? So here you see what we did was we switched 2 and 3. Right? That's like interchanging 2 rows, I hope so. Or interchanging 2 columns, right? This column and this column were switched to become this column here. That column became here, this column. That means the determinants are minus of each other. Because the permutation used to get from here to here, this has odd parity.
Yes.
Exactly what happens in complete generality over any ring, any dimension, and any number of indices. So let me write that down. And I explained this in the notes in the handout. So yeah. I just say that. So you split the summation into 2 parts. So split this summation into 2 parts. One part includes keeping track of which set of indices occur, not in which order they occur. Now they are distinct, so they are all distinct indices. Which set? So here the set is 1, 2, and 3 in some order. And then inside that, you split according to what order they occur. So split this sum. This is just an example for 3 cross 3, but the proof continues there. Split this sum into, first of all, the outer sum, which set of m indices JL. So now I write it not as an ordered pair or an ordered triple, but as a set occurred. And then secondly, maybe I need a different pen now. So I will use that. In which order do these indices occur? Because as we said, 3, 1, 2 is a different order triple for this than 2, 1, 3. And so you must count all 6 of them separately. But first of all, I will say, let's look at the set 1, 2, 3, and then look at the 6 different orders as the inside summation. Okay. So now we get, therefore, this is equal to. So we are continuing the calculation. Remember, the calculation started with determinant of A times B. And then we did all these things, we did up to here, and now we get equal to. Okay, so now the first question, how do you keep track of them? You have to choose one of them. You have to choose one of these 6 things and say, okay, I look at this set. The easiest way to say it is fine. These indices, let's write them down, let's list them in the set in increasing order. Okay, so let's say summation J in, let's let me put it this way. J1 dot 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 Jm. So now I'm writing it as a set, not as a tuple, and such that J1, so 1 is less equals J1. So look at 1 less equals is mentioned here, less than dot dot dot, less than Jm. Let me remind you again that m was less equals n, so indeed you can have n different elements in this set. This is the outer sum, and then as I said, inside it, you must take the inner sum. And now here you have to write down all the possible, for these 3 elements set, you need 6 ways. For m elements set, you need m factorial ways, which is the symmetric group of permutations. And now we can write this, right? So, okay, and now when we do that, what do you get? So first of all, you get this thing, bj11, bj22. Okay, and then you would get a permutation sign. You would get a, so this I'm going to jump steps here. So I will leave it to you guys to figure out. But what you get then here is you would get the rows of A arranged according to the permutation. But that is the same as saying I look at my original matrix, that of A, I, and J, L, but with the J's in increasing order, and I must multiply it by -1 to the by the determinant of sigma, or -1 to the sigma. I don't know how you write down permutations. I write them down as -1 to the length of sigma, or the parity of sigma. Okay. I think in linear algebra we write it as sine of sigma, right? SG. This is how one gets this. But now you see this determinant now no longer depends on the permutation. So I can take it outside. So the point is, again, this part, this whole part here is actually the permuted determinant here with the columns switched around. Okay, that sigma tells you how the columns are switched around. So this, as I said, I will leave it to you guys to figure out, to work out on your own. Maybe if nothing else, then take some example, 3x3 example, and work it out in the 3x3 example. Okay. But now finally then I can say this is equal to. So now this I will just write, instead of saying J1, J2, Jm, I will just say J contained in n of size n. And I write a determinant of A. Now what is I goes from 1 to n. That means it takes all the rows of E. And the J's are contained in J's. This is A, n cross J. That is exactly this expression here. Times, now I write down the summation. So sigma in Sn, and then this. So first of all, -1 to the sine sigma. Then the product of this. B, let's say L goes from 1 to n, B, J, L. No. B sigma J L I. That's what it is. Let's say L.
Excuse me. Excuse me.
Yes, go ahead.
When they have taken this summation,
Okay.
are you not mentioning over this summation over J? Are you not mentioning anything about this ordering of J, like J1, J2, Jm? No, in the next step, when you have written it as A.
And the convention is I'm just writing it down. So this is, if I write down the set 3, 1, 2 as a set and 1, 2, 3 as a set. And yeah, basically maybe I should mention the J1, J2, Jm here. Here maybe what we wanted to say was that's right. So
yeah, my question is that this condition is not yet lifted, right?
You are right. That's right. And now when you look at finance, that's right. So you still, because you have the J's, JLs, therefore you must still mention this. But now when you work this out, this is exactly the definition of the determinant of B J cross. So that is the Cauchy-Binet formula. Okay, so that's just the Cauchy-Binet formula so far. So yeah, but this is the end of the proof of that. The determinant of A times B.
So can you please explain this B summation determinant B part again?
Say that again.
Yeah, this determinant B part, can you please explain again?
This is the usual definition of determinant, right? You expand over all permutations of products.
Oh, okay, okay.
That's
Yeah, yeah, I got it. Sorry.
Again, this is an exercise more in keeping track of summations and notation than actual determinants. We just use the definition of the determinant and some multilinearity and take some summation outside it. But really, it's really the exercise is to how to keep track of all the how to visualize it. This is actually the determinant. This is actually this. It's just the visualization, but the mathematics is not. Yeah, but this is just the definition of the determinant in the usual way. When you expand along some row and then inductively expand each minor along the row inside it and so on, you get exactly this. Okay, so this was the Cauchy-Binet formula. Maybe the proof is not as important as the formula itself, which we saw how to apply to 1 cross m times n cross 1, n cross 1, or just m equals n when there is only one thing in the summation, or or even if you have 2 cross 3 and 3 cross 2, you have to take pairs of columns at a time, or m tuples of columns from the first matrix and the same m tuples of rows from the next matrix. Okay, I think I'm going to score this. So that is anyway, fine. So let's quickly finish this and then start with the density. Okay, so so now that was the Cauchy-Binet formula, but remember we wanted to prove the proposition that that the product of two totally non-negative or totally positive matrices is totally positive outcome. So proof of proposition. This is literally 2 minutes or maybe less. So we wanted to prove that, let's say I'll just do the total positive thing. So, and here A was m cross n and B was n cross Q. Okay. So, I need to look at all the determinants, all the minors that can occur inside A times B. A times B is m cross K. Okay, so proof. So, remember, I don't know if you remember, but we use P for the size of the square minors. So we need to take a minor that's less than m and less than k. So let me say it's less than the minimum of n comma. And look at some, consider some p many rows of A and p many columns of A. And choose subsets. Let's call them I of containing m and k K of size P. Then what is the determinant of this? We want to show that you start with, first of all, you start with the minor, you start with this matrix. You take the sub matrix where the rows are indexed by I and the columns are indexed by K. This is a P cross P sub matrix because the sizes are P. We want to show that the determinant of this minor is positive for every choice of I and every choice of K. So choose arbitrary subsets. There is no restriction on that choice. We want to show that this is positive. Assuming that these two are totally positive, we want to show this is totally positive. So every minor must be positive. How do you show that? So now you literally apply.
Hello, sir.
Yeah.
So here we don't have any restrictions. Like if we choose third column, we should choose the same third row. No restrictions like that. It could be arbitrary.
You choose a subset of size P. So of course you have to have distinct sets, and you will always write those sets in increasing order. When you take a submatrix of a matrix, you never reverse the order of the rows of the columns, right? You don't take the second row first and the first row next. You take
No, not about the ordering. Not ordering is fine.
You never take the same row. You take distinct rows and distinct columns.
Yeah, okay, yeah, that's what I was. Yeah.
When you take a submatrix, you don't mess around with the order or the repetition. You take one row exactly once and make them occur in the correct order.
Yeah. Okay. Thank you.
Okay. This is the submatrix. Okay. Then by Cauchy-Binet, I will just say C minus B. This means Cauchy-Binet formula. This is the summation. And why did I choose I and K? Because of course I want to choose a J here. The same J there. K in N, and the size of J is B. This is going to be very interesting. Okay, fine. So first of all, I'll write down the determinant of A, I cross J. Determinant of space. So determinant of A, I cross J times determinant of B, J cross J. And here the sum goes over J equals B, J continuous. Okay, so now here is the interesting question, right? Okay, so what I want to say is obvious, right? I want to say, well, A is totally positive. So this matrix is, this determinant is strictly positive. This determinant is strictly positive. And therefore the product is strictly positive. If you add up positive numbers, you get positive. So this is what's the small gap I need to address? This argument. Okay, the small gap, okay, fine. The small gap is I'm going to change this to totally non-negative and let you guys figure out totally positive. Right. That's the easiest way because we are running slightly shorter, slower time. So suppose these are totally non-negative and I want to prove the product is totally non-negative. Then again, the calculation is exactly the same. But now you see, these are minors of A and of B. They are totally non-negative. So the determinants are non-negative. And the sum is non-empty, or it could be empty. If the sum is empty, you get 0. That's fine. If the sum is non-empty, you get a non-empty sum of non-negative numbers. Either way, this whole thing is zero. For all I n. That is why the product is totally now, so this is the correction I should have made. And I think maybe there's a typo. It should have been max. It should be min. N is less equals min, first of all. So okay, what is the problem for total positivity? The problem is very simple. Either the sum can be empty. How can the sum be empty? The sum can be empty if P is strictly bigger than N. For the TP version, total positive analog. What happens if P is bigger than N? So things like so for example, you have a matrix A 3 cross 1, B 1 cross 3, right? And this is TP because the entries are all positive. This is TP, the entries are all positive. But you see, we already talked about this, right? These two matrices are totally positive, but this has rank at most 1 and this has rank at most 1. So you can never have the fact that they can't multiply and give you a full, the product has also rank at most 1. So if you put the product is 3 cross 3, so the determinant and all the 2 by 2 minors must be 0. So the product of these two totally positive matrices is not totally positive. So the proposition should be actually corrected. And yeah, so but the point is 1, and even if this was a 2, that 1 is less than this, and that is why you have a problem. So whatever this 1 is, this 1 or this n should be at least as big as the minimum value of m. So the further need to assume further. N is bigger equals min of m and t. Once you assume that, then this sum is of course non-empty because this min m and k is bigger equals p. So n is bigger equals p. So of course you can choose elements of size p. And once this sum is non-empty, then you can take these things and you're done. So that's the only extra assumption. Fine. This is actually good because I should make the correction in my notes as well and then upload a fresh version. Okay, let's see this correction. It should be min. Here, statement should have min. So yeah, so the proposition should be modified to say n is bigger equals min. Okay, great. Okay, so that's the end of the first section, and we did a little bit of the second section yesterday as well. But yeah, once you have this, once you have the fact that the summation is non-empty, but each of these guys exists and is strictly positive. Strictly positive. So you are adding up a positive number of positive numbers, and that is a positive number. It's all minors that you can compute that do exist are strictly positive. So the product of two EP matrices is higher. Otherwise, it's just Tn, but not T. Okay, so these were some basic properties of totally positive matrices, some basic examples, how to work with them, and Cauchy-Binet formula. Now, what I want to do is the next statement that we'll do. The plan was in the second lecture, we will discuss the density. Let's talk about density. I think that is right. Next thing. Yeah. So there are 3 examples here. I'll just mention some density. Actually, before that, I need to give you a definition. So the definition is the following. Given p, an integer bigger equals 1, let's say, let me not say p, let me say k. A matrix A in R to the n cross n is totally non-negative or of order k. We write this as T and K. Or do I want to say P itself? Maybe I should say fine, I'll just say P. I'll write it down explicitly. We'll say T and K. All this means is I don't need to check every possible, all minors of every size. I only check the 1 by 1, 2 by 2, and 3 by 3 numbers. And it is if all those are non-negative, but any positions from the matrix, then the matrix is totally non-negative over 3. If the 1 by 1, 2 by 2, 3 by 3, 4 by 4 minors are positive, then it's totally positive of order 4, and so on. If all 1 cross 1, 2 cross 2, p cross p minus, okay, and this is non-negative, so this is R bigger equals 0. Similarly, I won't write down the formal definition, but just use the word here, here, and here. PPP. So now, for example, the Cauchy-Binet formula actually can be updated as well. Right? So, e.g., the Cauchy-Binet formula. Sorry, not the Cauchy-Binet formula, but this application. In fact, proves more generally if A and B, yes, okay, I'll say A is n cross n, and B is n cross k. If A and B are totally non-negative of order P, then so is A. Two points. First of all, why is this true? And second of all, why is this more general than the fact? First of all, why is this true? This is true because of the same calculation. Look at AB, I cross K. So here I still assume that the size is now less equal. We want to only look at the minors whose size is less than B. So I can, for example, call it, let's say, I'll call this P naught. Now when I take the product of and subsets of size less equals P, because the subsets of size less equals P, here this is a matrix of size between 1 cross 1 and P cross P. So its determinant is non-negative. And this is a matrix of the same size, so its determinant is non-negative. By assumption, because both A and B are assumed to be Tn for all sizes smaller than P. And this P naught is smaller than P. So again, you are still adding up a product of non-negative numbers, and of course you have to non-negative. So the proof is exactly the same, nothing changes. But you just look at matrices until a certain size, and if those are positive for A and B, then are non-negative, then that is non-negative for A times B. That is the first reason. The proof doesn't change at all. And why is this more general? Because I can choose P. If I choose P to be like infinity, or if I choose P to be the largest, if I choose P to be this number here, then this matrix being Tn of size P is the same as being Tn. Okay? So it implies it. So this statement is a special case of this. For example, tell you how. So for example, I can say, I can look at the matrix, let's say 1, 2, 3, 5, 9, 1. This is a matrix. It is a 2 cross 3 matrix. So one can ask if it's totally non-negative of size 1. It is. All the entries are positive. Is it totally non-negative of size 2? It actually turns out it isn't. But sorry. Okay. But and then totally non-negative of size 3 and 4 and so on. That's the same as totally non-negative of size 2. Because there are no 3 by 3 minors to check. Not size, totally non-negative of order 3. There are no 3 by 3 minors to check. There are no 4 by 4 minors to check. There's nothing else to check. So the condition that all 1 cross 1 and 2 cross 2 minors are non-negative, and all 1 cross 1, 2 cross 2, and 3 cross 3 minors are non-negative, are the same condition because there are no 3 cross 3 minors. So that is why proving it for a fixed size or for everything up till a certain size, if you can say that for all possible P, then that's a more general statement than just saying it for the full matrix. Because you might have matrices which are Pn1 but not Pn2, and yet you can say something about the product of two such matrices. But this one just says either the matrix is completely Tn or it is not. This says it size by size. So you are refining this statement. Okay, so that's what Tn3 matrix is. This is Tn1. Totally non-negative order 1. In fact, this is Pt1, but not Tn2. Not. That's just an example of this definition. Okay, so now let us get to density. Fine. I definitely have time to state the theorem and let's see how much of the proof we can do. Luckily, I did some of the proof last time. Okay, so density, the first statement is what does density mean? So it means the following. So for example, if you look at positive, so you, again, if you have seen positive semi-definite and positive definite matrices, actually forget that. Rational numbers are dense in reals. So everybody knows what that means. It means that take any real number, you can approximate it by a sequence of rational numbers. In the matrix world, let me tell you something nice. Positive definite matrices. Matrices whose eigenvalues are all strictly positive and are real symmetric matrices are dense in positive semi-definite matrices, which I remember I abbreviated last time, PS. So if you know the spectral theorem, then you can actually prove this, and this is one of the tutorial problems. Okay, so now what I want to say is that, in fact, we should be thinking of these totally non-negative and totally positive matrices as analogous to these guys, and that analogous density statement. So this statement is completely easy. There's nothing to do, and this was probably known for 100, at least 100 years, or to Sylvester in the 1850s or something. The next statement was proved in the 1950s. So this is the statement called Whitney's density theorem for total positivity. And so here we will say the following. So okay, I should have said n cross n. I'm going to fix the sign, right? Okay. Now this is for positive, semi-definite, and definite. Those are symmetric matrices. But as we said, total non-negativity doesn't require square matrices. It can be rectangular. So I can look at rectangular n cross n matrices and ask if inside there, totally positive n cross n matrices are dense inside totally non-negative. The answer turns out to be yes. But you can do even better. You can refine it by the size of what size minors you want it to be positive or non-negative. I can ask for total non-negativity of size p. So given integers m, n, and p. So this is Whitney's theorem. Whitney density theorem. I should point out, by the way, this is Anne Whitney. So she was a student of Schoenberg, who invented splines, as I told you. There is a Fields medalist called Hassler Whitney, and this is not the same person. This is Anne Whitney. That is H Whitney. This is A. Okay, so given integers m, n, and p, I guess. And I could take even p to be less equals n times n. Even integers m, comma n bigger equals p. So I only look at matrices whose 1 by 1, 2 by 2, and p by p minors are non-negative or positive. And the matrices, of course, have size bigger than the p, so that there's no vacuous. No, they're actually using some meaningful determinants. Bigger than 0. Right? The space, the set of totally non-negative p, sorry, totally positive p, EP of order p, m cross n matrices is dense in all TNN, TNP, m cross n matrices. Okay, so that's the statement. So indeed, the same kind of density theorem holds, density holds phenomenon, and we want to
Excuse me, sir.
go ahead.
Sir, you write the statement that given integer for mn greater than p, which is again positive, the set of all totally positive p mn
Order P, yes.
is
Yeah.
rectangular matrices or a square. We have to take it as a square matrix for totally positive matrices.
No, m cross n matrices.
Okay.
So m cross n matrices. And so, for example, let's take p equals 3. Right? So what I'm saying is take any matrix whose cross, take any n by n matrix, all of
Right.
those entries are non-negative, those 2 by 2 minors are non-negative, and 3 by 3 minors are non-negative. P equals 3. The matrix can have size 500 by 3 or 500 by 500 or anything. M cross N matrix is 1 by 1, 2 by 2, and 3 by 3 minors are non-negative. You can find a sequence of real matrices converging at each entry, M cross N real matrices converging at each entry to this given matrix, whose 1 by 1 minors are positive, 2 by 2 minors are positive, and 3 by 3 minors are positive. But the limiting one has these minors as non-negative. That's right. So the space of TP of order P matrices is dense in En of order P.
Okay. Right.
That's what the statement is. So we have to build up this fact that this matrix. So you can start by so for example, if you take P equals 1, then every matrix with non-negative entries can be approximated by matrices with positive entries. That is just obvious. So I can take what for example, I have the 0 matrix. Actually, fine. Let me write. So for example, if P equals 1, then I don't. So it may be that my original matrix actually had positive 2 by 2 minors as well. But I just care about the fact that I want to approximate it by matrices with positive 1 by 1. Then how do I approximate this matrix? Well, it's very simple. What you do is you write down A plus 1 over, let's say, 1 over K times the 1 matrix. This is my matrix A. Now, because we just care about the 1 cross 1 minus, the entries here are non-negative. And to each entry, I'm adding a positive real number, 1 over K. So, of course, all the entries become positive. So, of course, this guy is TP1. And as K goes to infinity, obviously, this just goes away and you get your original matrix. So, for P equals 1, this is just a trivial consequence of the fact that positive real numbers are dense in non-negative real numbers. So that is just trivial. But it's really the full statement that is the key. Okay. So we have 8 minutes, so 10 minutes. So let's start with a little bit. Okay, so now let's start with the Whitney density theorem. So the way we will do it is we start with a matrix A, which is M cross N and P and P. And I will also fix the rank of that matrix. So this is, I think, Whitney's school from 1951. 1951 or 1950. I'll just say 1950s. For safety, the proof. So start with the matrix. So let A M cross N P T N P of rank R of. So we will also need to work with the rank. So we'll start by fixing the rank. Okay. Let me also now define the following matrix. So remember we proved last time this lemma of Polyak, which is that the Gaussian kernel is totally positive. Right? So define, let's see, so I want, so first of all, given sigma, which is a positive variance parameter, I'll use sigma and not sigma square. Maybe so sigma bigger than 0, I use sigma in real interval 0 to infinity, and an integer m will be equals 1. Define this matrix G for Gaussian. This is in R to the m cross n, and this is literally equal to that e power minus sigma j minus a square. Sigma times. Notice that this matrix is, of course, real, symmetric, and totally positive. It's totally positive by the lemma. By last lecture. Okay, and now I'm going to define, given this A, I will define A of sigma to be the following. I take my matrix A, at P multiplied, this is M cross N, So I pre-multiply by an m cross m matrix, and then I post-multiply by n cross n matrix. In the same statement. Okay, first of all, okay, also, what as if sigma goes to infinity, can you tell me what this matrix goes to? Right, this here. What is the diagonal entry of this matrix? Diagonal entry.
1.
1. Right? Because j minus k is 0, independent of sigma, the diagonal entries are 1. The off diagonal entries are e power minus sigma times some positive number. So as sigma goes to infinity, the diagonal entries don't change, they stay at 1. The off diagonal entries all go to 0. So this matrix goes to the identity matrix. So I'll write down both. This is PP by last class, last lecture. And secondly, G sigma comma n goes to identity n by n as sigma goes to infinity. So these two facts will leave. Okay, look at this thing. So I'll basically my plan is okay. Yes. Okay, so define first of all this matrix. Now because G sigma goes to identity, as sigma goes to infinity, what does this go to? Identity times A times identity. This goes to A. So we are going to do some kind of limiting thing, right? So instead of sigma, I will write it 1 over K or 1 over. Yeah. So basically I will take a sequence of matrices by this construction and iterating this construction a few times that to get to my A1. So I think I should really call this matrix A0. I think. Maybe I will do that on the next page. Okay, anyway. So first of all, what do we know? We know that A was totally non-negative, order P and rank R. These guys, what do we know about the ranks? Well, this is totally positive. It is square. So its determinant is also positive. So it has full rank. So therefore, if you multiply by invertible matrices, you don't change the rank. So this is also of rank R. And it is also of size m cross n because matrix, square matrices. What can we say about the total non-negativity part? Is it still totally non-negative of order P? I know this is m cross n. As rank R. Because this is totally positive. Hence invertible. So if you multiply by invertible matrices, you don't change the rank. But I'm asking you if this matrix is totally positive, non-negative of order P or not. The answer is yes, it is. Because that was
Previous theorem, proposition.
that's right. The previous proposition says that if you take any product of P and P matrices, then you still get a P and P. Right? But I wrote it down somewhere and it is now here. So, yeah, exactly. And is P and P by the previous proposition. Good. What's going on? Okay. So now the claim is the following. This is the claim. So what we are going to do is we are going to build up the order of total positivity. Okay. So remember, I want to approximate this matrix by a TP2 matrix. So far there is no total positivity mentioned anywhere. We are going to start mentioning it now, and we are going to build up the order of total positivity until we get to PPP. That's where we want to get. And then we are going to say this entire procedure can be repeated with smaller and split larger and larger sigmas, and that would bring the whole thing down to 8. Okay, the first claim then is 8 sigma. So not A itself. A you have no control over it. A could be the zero matrix. Everything can be zero. That certainly is TNP. It is TN, but it is TNP. But A sigma you start slowly getting control over. A of sigma is TP of order minimum Rn. That's the correct statement. Yeah. Okay, let me prove this until here, and then we will stop today. And then I will we will continue tomorrow, so on Saturday. So I won't erase this part. I will just change the statement. I'll write the statement there, and then we'll rehash this part and then finish the proof next. And then move on to the step. Okay, so how do you prove that something total positivity happens? You take a minor of size less equals that number, and then you start to calculate. Okay? So prove that 1 less equals s for the size less equals this number, and then look at the minors. So let's see. I'm calling it J and K. J contained in M, K contained in N, have size S. And now we calculate this A sigma J cross K, right? So the determinant of A sigma. So you want to prove that this matrix is TP of that size. So for every size smaller than that size, you calculate and you prove that the determinant is positive. So we must prove that this is positive. Fine. So what is A sigma? A sigma is this. We'll start writing this down. So it is the determinant of this. So J cross something here, something cross something here, and something cross K. Right? That's how we do Cauchy-Binet formula. So Cauchy-Binet. But now Cauchy-Binet was for product of 2 matrices. But obviously you can then extend it to a product of 3 matrices, right? Because it says determinant of ABC. If I had this, I would say the determinant of AB, I cross J, times determinant of C, J cross K. Then you take summation over J. But now instead of AB here, I can do Cauchy-Binet for this. And I can take summation over J and J prime. I would get determinant of A, J, J prime, then determinant, sorry, I, J prime, determinant of B, J prime J, and then determinant of C, J K. So I would just do Cauchy-Binet one after the other. That's exactly what I do here. It's the summation with, let's see, I'm going to call them L and M contained in whatever. L and M. L and M are contained in here. Size is equal to S. Okay, so determinant of, now we write the whole thing. Maybe I will write it on the next line. Summation L and M are contained in the set 1 through minimum of R comma P, and the sizes are equal to S. Because all sizes are square. Everything here is square. So all sizes must be the same size as S. So it is determinant G is sigma M I no, J cross L, J times L, then determinant of A L cross M, determinant of G sigma N, M cross K. Just using this Cauchy-Binet formula, which I will not use. Okay, now let me finish the fact that it's positive and then we will stop. Okay, now clearly this number is positive. Okay, and then clearly this number is positive. And now let's look at this number. Right? So we know that A is totally non-negative of size this much. But I want to claim that at least one of these A's is strictly positive. Why is that? I claim that this A L cross M is strictly positive for at least one minor. Why? Because if all of the determinants of size R cross R or smaller than that are 0 in A, then the rank of A is less than that. So if you know this, I hope you know this result. That if all the 5 by 5 minors of a matrix are 0, then the matrix cannot have rank 5, it has to have rank 4. If all the k by k minors of the matrix are 0, the rank of the matrix is less than 5. So well, this is less equals R. So if all minors of this size of A are 0, then A has to have rank whatever. A cannot have that rank. A cannot have rank R. So A has to have rank strictly less than this number, which is less equals R. So at least one. Since rank of A is R. So I have a sum over these numbers, and of course A is totally non-negative until this order. So all minors here are non-negative. So semicolon, all of these are non-negative. So you really need R and P because the R comes to the rescue to tell you that at least one minor is positive. The P comes to the rescue to say all the others are non-negative. So you need both R and P to help you here. But they do. And once they do, you know that this is a sum of our non-negative numbers, positive and non-negative. It's a sum, and at least one of these numbers exists which is positive. So first of all, the sum is non-empty because there is such a positive number. And for that positive number, you get a strictly positive product. Everything else is non-negative. Therefore, this is. Okay, so that's where we stop. So this is the end of the proof of the claim. We will continue with the proof of Whitney density next time. But right now, you see, already we have at least gone from the total non-negativity of the matrix A to doing some interesting perturbation. And that perturbed matrix is totally positive now of a certain order. So we at least have raised positivity, the order of total positivity to something. Next time, we will see how to tweak this in just one entry, in the corner entry, and make this totally positive of a larger size, or one larger size. Then you again tweak it and you make it totally positive of two larger size, and again and again and again, until you get to the total positivity of the level that you want. And at each step, you just do some like each step, you just pre and post multiply by this kind of a thing. So therefore, you don't actually end up. So therefore, then as sigma goes to infinity, you still end up at each step going back to E. So anyway, that's where we are going next time. So for now, I will stop. And we will finish on Saturday. So we will do this for sure. And then, so my plan is I will tell you how to prove this, how to prove this theorem about the eigenvalues of totally positive matrices and totally non-negative matrices. The one thing I may not do is the proof of Perron's theorem, but the proof is written out there. And if we have time, we will do it. If not, then I will at least do everything else. Okay, so I guess we will make